Hello, everyone. Thank you all so much for inviting me and for coming out. I know it's cold for Portland. I really appreciate all the support. So this is a talk on how the internet works. And just who am I? I am a director for the Python Software Foundation. I'm also an organizer for Boston Python, which is actually the largest Python user group in the world, with over 4,000 members at this point. Oh, thank you. And I also, I run a software startup in Boston, and we use Python every day at work. So I'm very invested in the Python community. This talk is fairly language agnostic, though. So if you're not a Python person, that's totally fine. And the internet is probably my favorite technical topic of discussion of all time. So I'm very happy to get to share this with you. So while this is mostly an excuse for me to impart my love of networking to you all, we are nominally going to answer this question tonight. So I pull up Firefox, I'm at home, I pull up a web browser and I type http://python.org into the browser bar and I press return. What actually happens at a networking level to get the python.org homepage displayed on my screen? So that's the question we're going to answer. That's what it looks like, in case you're wondering. I'll argue that this is at least 4 distinct questions. So one question is, what is python.org? Like, conceptually, existentially, what is that? Where is python.org out in the physical universe? How does my computer talk to python.org, whatever it is? And once they're talking, what do they actually say to each other? So we're going to investigate each of these questions in turn in this talk. And while we're going through this discussion, we're going to talk about a number of specific internet protocols. And a protocol is just a format and rules for exchanging information. That's all that means. There are a lot of different protocols that make up the internet. And in general, internet protocols are layered. They each do one thing, and they do it well, and we put them together to get useful work done. OK, so our first question was, what is python.org? And there's a protocol to answer exactly this question. Python.org is a domain. It is a human-readable, memorable way of pointing to a particular computer out on the internet. And humans are good at thinking about words, but computers are better at thinking about numbers. So there's a service, there's a protocol called the Domain Name Service that translates these host names or domains to IP addresses, which are just unique numbers out on the internet. So for example, python.org maps to, using this DNS protocol, the IP address 82.94.164.162. And so what literally happens every time you visit a new web page is before you have anything to do with that specific web page, you have to figure out what the IP address for that associated computer is. So when I want to go to python.org, before I do anything, my computer asks a DNS resolver, a service whose whole job is to perform this DNS lookup. I say, hey, DNS resolver, what is the IP address associated with python.org? And it sends back a response containing the IP address, and I can then use that IP address in subsequent queries out on the internet. So DNS is a prerequisite to doing anything else on the internet, so it's definitely a critical protocol for us tonight. So that was question number 1. Question number 2 is, where is python.org? Unfortunately, there's a protocol dedicated to exactly this question as well. This is the Internet Protocol, or IP, which is the same IP from IP address from before. So the Internet Protocol's job is to handle addressing and routing on the internet. So I don't have a direct line to python.org. Like, when people talk about the internet, what are they really talking about? They're talking about this gigantic network of physical hardware, this gigantic, sort of matrix of machines that talk to each other to get data that I send, packets that I send from point A, myself, to point B somewhere else on the internet. So there are all kinds of computers or routers out on the internet that my data needs to travel through to eventually get to a destination. And IP deals with how you decide what path to take. A really good way to understand the work that is going on under the hood using IP is to use a utility in Python called Scapy. So if we start up Scapy, we get a little interactive prompt. And what we can do is we can use a built-in SCAPI facility called traceroute that is going to show us, it's going to expose to us each of these intermediate hops through the internet that IP is telling us to take when I make requests to remote machines, when I make requests out on the internet. And so this spewed out a bunch of data. That was kind of fast, so let's drill down on the important parts. So here's the same data with a little bit of annotation from me. We have two columns here. On the left, we have IP addresses. And on the right, we have host names. These are exactly the host names that DNS would care about, the IP addresses and the host names that DNS would care about from before. At the top is me, at home in Boston. And at the bottom is the machine, the actual physical hardware, the IP address associated with python.org. And each of these lines represents a hop through the internet, a distinct machine, a distinct router through which my data has to travel to get from point A to point B. So this is actually kind of a lot of work going on under the hood, right? I mean, I definitely don't have a direct line. I had to take 15 hops to get to python.org, wherever that is. We can do even more stuff with this data, though. So one of the cool things built into SCAPI is we can visualize this graph of the path that I took through the internet. So we did that. The bottom line there has us doing the visualization. And here's the output. Here's the zoomed out output. And again, I'm at the top, and python.org is at the bottom. What we see here are a sequence of colored circles. Each circle represents a router, a physical machine out on the internet that my packets travel through. And each color represents a different company, a different internet service provider that manages that IP address and that hardware. So for example, when I started at home, I happened to get my internet through Comcast. So we see that my packets go through a couple of Comcast networks at first. Then we go through another really big ISP, Cogent. We go through IS. And then finally, we get to python.org. So that's pretty amazing. It's pretty amazing that all of these companies are sort of working in concert to allow my packets to get to an arbitrary place on the internet. I mean, there's a lot of political engineering going on to make sure that this just works seamlessly most of the time. So that's cool. It's cool to know who sort of owns the hardware that my data is going through. We can do one better, though. What if we wanted to know where physically on this planet that hardware lived? Like, what if we wanted to know where python.org, the hardware, lives? Well, we can figure this out. We can use a geolocation service. So you can pay companies, or there are some free services where they have done a bunch of work to sort of triangulate where each of the IP addresses on the internet is. And we can use an API for one of those services to figure out, based on the IP address, the approximate location of the physical hardware. So I don't know if any of you have a guess for where python.org lives. Any guesses? New York, Boston, somewhere in Europe. Okay. Oh, okay. So a lot of potential here. So here we go. So we have a list of these traceroute IP addresses. I found a really simple free geolocation service. They give a really simple Python API to do the lookup. And I just print out some of the location information for each of these IP addresses. And here's what we get. The Amsterdam folks. You had some inside information, I think. OK, great. So if we run this little geolocation script, we see for each of these hops, I did, in fact, run this starting in Boston. My packets go through a couple of places outside of Boston, get to New York, somehow get across the Atlantic to London, and then from there get to Amsterdam. So that's a pretty amazing journey that happens every time I request something on the internet and every time I get a response back. This journey is taken. And it basically works without us noticing. So what about that New York to London trip? I mean, like, how is that working? It's worth dwelling for a moment on the fact that companies, at some point, laid cables, like giant, shark-proof, anchor dredging through the sand-proof cables under the Atlantic Ocean to enable us to have phone calls and internet communication go between the US and Europe. Again, that's some amazing, not only software engineering, but hardware engineering, but political engineering for this to basically work. We do occasionally hear about underwater cable cuts, reducing internet access to, and typically places that have less dense connectivity, often places in Africa that still maybe only have one line. It literally happens sometimes, though, that like some pissed off guy with a backhoe severs like the one connection between a country in southern Africa and the rest of the world, and they don't have internet until someone fixes the physical hardware. That's awesome. Like, I mean, it's not awesome that Africa can lose internet sometimes when people do that, but it's amazing that there's this system that heals pretty quickly that basically works. OK, so that was kind of a roundabout answer to the question, where is Python.org? But we actually have a really concrete answer now. We know that the hardware hosting the actual Python.org is in Amsterdam. And we know the path that my packets take through the internet to get from Boston to that hardware and back again. So our next question is, how does my computer talk to Python.org? And the answer is that it talks reliably using a protocol called TCP, the Transmission Control Protocol. And what do I mean by reliably? Well, as it happens, while mostly things work, while mostly these hops to the internet succeed, and I'm able to talk to machines out on the internet, sometimes the data gets lost. Sometimes the data gets corrupted. Sometimes at one of these intermediate routers, they get too full of data. There are too many packets queued up to be processed, so it drops new ones on the floor. Sometimes you're just sitting next to a really strong microwave, and that screws up the Wi-Fi signal. Like, lots of things can happen to cause data to not successfully get transmitted. And folks through the years discovered that it would be useful to have a protocol that would retransmit corrupted or lost packets. And so TCP does that. It will deal with retransmitting packets that don't get acknowledged by the remote service in time, and a bunch of other things to make sure that you have a nice steady stream of ordered packets ending up at the destination. So TCP is a really good idea. We use this all the time, actually. This idea of a reliable protocol ends up being really useful out on the internet. So for example, when you browse the web, when you are chatting with someone, when you are checking your mail, all of these things use TCP as an underlying reliable transport mechanism. And there's an application layer protocol that sits on top of it that does the specific application work that you care about, like email stuff or chat stuff. So if you remember from that diagram earlier, we talked about internet protocols being layered. This is a really good example of that. We get this reliable layer that we can build stuff on top of. Now, this sort of begs an interesting question. So, like, let's say that Python.org wants to be able, the hardware for Python.org wants to be able to have multiple services running on it with a single IP address. Like, maybe it wants to be a web server, but you also should be able to check your mail through Python.org, or you also want to be able to chat through Python.org. And they all use TCP to the same IP address. So how do you disambiguate the different streams of data? So the way that we do this is we pick a special number, like sort of a default number, we call it a port number, that we associate with each protocol. And that gets sent in the packets of information. It's some metadata on the packets of information that we send, so that we know via the port which application is supposed to care about these packets. So now when we're talking over TCP, we actually, in addition to having information about where we're going, we also say what port we're using, so we know what the application is. So that's all that a port is. It's just a special number associated with each application. And so how do we talk to Python.org? We talk reliably using TCP. So one last question then. What does my computer say to Python.org? And this is perhaps the most familiar protocol name. We talk about the web, about the internet, using HTTP, the Hypertext Transfer Protocol. And this is what clients, like my laptop, my machine, use to request resources from servers. So when you type in that http://python.org, or sometimes these days the browser does it for you at this point, that's what the HTTP stands for. We are specifying the application layer protocol that my computer is going to use to talk to the remote service. And I said that we request resources. What is a resource? It can really be just about anything, but commonly it's an HTML web page. If you're writing APIs, maybe it's JSON, maybe it's dynamically generated data. Like if I go to whattimeisit.com, it computes on the fly what the actual time is and spits it back out at me. So a resource can really be anything, but it's the thing that you request from a server when you talk HTTP. So one of the really cool things about HTTP is that it's a pretty simple protocol. It's textual, it's human readable, it's line delimited, which means that it's pretty easy to, if we wanted to, inspect the way the protocol looks and even pretend to be our own web browser. And so why don't we go ahead and do that using a really simple utility that's probably installed on all of your machines right now called Telnet. So let's pretend to be a web browser by using Telnet to connect to python.org on the default port for the web, for HTTP requests, port 80. So we make this connection, and then we're going to make a request we're going to get /, which is the root resource, sort of the default page that you get when you visit that hostname. We provide some additional metadata that's part of the protocol, and then we get back a response from the server containing whatever the resource was that we requested, in this case, an HTML web page. And that flew by quickly, so let's drill down on the important bits. No? There we go. Great. OK, so we use Telnet to connect to python.org on port 80. What is the very first thing that we actually did? That thing from before, right? We did a DNS resolution. We had to map that host name to an IP address before we can actually use that IP address to do something productive. I wasn't kidding. We really do that. Once we have that IP address, we establish an underlying reliable TCP connection, and on top of that connection, we now get to speak HTTP. We issue a GET request for a particular resource. What we get back is, well, first we get back a status code saying what happened. In this case, it was a 200 OK. I understood the request and was able to respond to it. We get a bunch of useful metadata, useful headers containing things like when the content was last modified, the type of the content. In this case, it's HTML. And then we get the body, which contains your resource. In this case, it's an HTML web page. This is the HTML, the markup that your browser then renders to look like a pretty document that we see with our eyes when we view it in Firefox or Chrome. So that's pretty cool. It's not, it's very easy to do this using Telnet. And if you've ever used, in Python or in other languages, a library like urllib or requests or pycurl, and you've sucked down resources from the internet using these libraries, what Telnet is doing, what we did manually, is exactly what these libraries are doing under the hood. They're going to do that DNS resolution, and they're going to speak the HTTP protocol to fetch resources. And it's not an accident that the hypertext transfer protocol and the hypertext markup language share the same prefix. These are a protocol and a markup language that have a very intertwined history in the history of the internet. OK, so we got to pretend to be a web client. That was pretty easy. How about pretending to be a web server? Well, there are a lot of ways to do this in Python specifically, but in probably any language. My favorite way to do this is using a networking library called Twisted, because Twisted makes us able to do this in very few lines of code. So here is actually 99%, everything with the imports, 99% of a totally functional web server written in Python using Twisted that you could place on a machine out on the internet, and you could literally then connect to it with a web browser or a Telnet. Like this would actually respond to requests speaking HTTP. Now it's a very simple web server. All it does is echo back what you asked it, but it would be a web server nonetheless. So let's see what the important parts of this are. So first things first, we are in fact implementing a class that implements the HTTP protocol. It receives lines, and it responds with lines of data. The very first thing it responds with is that status code, 200 OK. And after that, it echoes back whatever you sent it. If we look towards the bottom, we see that there's this reactor thing which just says, hey, listen on a particular port for data. And when I get data on that port, respond to it as defined in this protocol. And so we see that we established this listening for TCP connections on port 80, the default port for web requests for HTTP. And then we say, OK, reactor, just do that forever. Sit in a loop forever, listening for requests and responding to them. Exactly what Google.com or Yahoo.com or eBay.com, all of these sites, that's what they're doing in a nutshell. Listening forever and then responding to requests. So that's pretty cool. I mean, it's cool that this idea of a web server can be expressed in one slide, essentially. That's all there is to it. So what does my computer say to python.org? Well, it talks HTTP. It talks HTTP to request resources that are then rendered by the browser into nice web pages that we browse. And those are our 4 questions. So we mostly have the whole story. So when we type this thing into our browser bar and press return, we know exactly what happens. The first thing we do is we do DNS resolution. We map a host name to an IP address. Armed with that IP address, we can rely on IP to deal with how my packets get from point A to point B. What is the route that my packets take through the internet? Our requests are delivered reliably thanks to TCP. And then in this case, because we're emulating a web browser, we request resources using the HTTP application layer protocol. So these 4 protocols in concert are the driving force behind what we do when we browse the web every day. Now, a really cool way to develop a greater understanding of what's going on here is to be able to inspect some real traffic in real time. And there's a great utility for doing this called Wireshark. So let's go ahead and check out what Wireshark does. So when you run Wireshark, it tells your computer to listen for any packets that it can hear. You know, it's on the Wi-Fi or it's on a wired network, and usually your computer is ignoring traffic that is not destined for it. But when you use Wireshark, you say, hey, anything that you can hear, I want you to report back to me. So when I was back at home, I turned Wireshark on and I said, okay, computer, I want you to tell me everything that you can hear for like 5 minutes. And I ended up capturing about 10,000 packets worth of data. So 10,000 things happened under the hood in the 5 minutes that I was sitting basically at home doing nothing with my laptop and a couple of other machines at home. So there's a ton of traffic going on in the background that you would never see if you weren't listening with a utility like this. So here are some of the things that I found. So first up, surfing the web. So I was doing whatever I was doing, looking some things up, and exactly the sort of the cycle that we talked about really does happen in real life. Time is going down here, and here we see the source IP, myself at home, the destination IP, where out on the internet I'm requesting resources from, what protocol is being spoken, and then the data from that protocol. And sure enough, when we see me, I was visiting the Boston Python website, we see, sure enough, first we do a DNS request, resolve that domain name to an IP address. We see the TCP handshake setting up that reliable connection. And then we see an HTTP GET request and a response for the data for the Boston Python homepage. So this really does happen. You really can see all the nitty-gritty details if you want using Wireshark. Another thing that I saw is that I was not actually at home alone, even though I thought I was. One thing I saw is that I have a printer who is very, very lonely. And what it does is periodically, without anybody really asking, it would shout to the world, hey, local home network, I'm a printer. Would anybody like to print to me? Not only did I have lonely printers, I also have a lonely TiVo, desperate for someone to watch Netflix. So perhaps the TiVo and the printer should get together. Another thing that I saw is errors. So even just locally at home, just browsing the web at home, the things you see in black are errors, are TCP packets that did not make it initially, and TCP is retransmitting. So errors really do happen, not all the time, but occasionally, and TCP really does take care of the retransmission. So that's pretty cool. Another thing that I saw was encrypted communication. So far, we talked about HTTP, and we saw with our own eyes that when you make these requests, it's all just human-readable text. And we saw that as both the client and the server. Sometimes you don't want random people snooping on your wireless, like people like me, randomly snooping on your wireless traffic to be able to see what you're doing. And so many protocols have been developed that are encrypted, that they scramble the data that you're sending using various mathematical properties so that eavesdroppers cannot tell what you sent. So there's an encrypted version of HTTP, HTTPS, which we've all probably used when banking, that establishes this encrypted channel. And we can see that whole setup in Wireshark as well. We can see doing this special handshake to agree on some secrets to use to encrypt the channel when I make my web requests. So that's pretty cool. Speaking of encryption, do people here use IRC? Yeah, maybe some people are on IRC right now. You know what's not an encrypted protocol by default without you doing some work? IRC. So for example, here's me, here's a little snapshot of a session of me connecting to the Freenode network to join and talk on some of my favorite open source project channels. So here's sort of the zoomed out view of me initiating logging on. And if we drill down here, Freenode, we see Freenode. Again, this is a line delimited, plain text, unencrypted protocol. It's saying, OK, your username is JessTess. What is your password? And you can see all of the content even in Wireshark. You can see the full prompt. And then you can see me responding with my password, which is Django for life. So if anybody would like to hop on Freenode right now and take advantage of that information, please do. But yeah, so IRC, unless you do some work, is not an encrypted protocol. And this is a good example of why it matters, right? It was very easy for us using Wireshark to take a look at this conversation. OK, so Wireshark, you should never do this in like a coffee shop. You should only do this at home, the privacy of a network that is under your control where this is OK to do. But it's an incredibly, many a Saturday morning have I spent, with my coffee, with Wireshark on, just seeing what's going on in the background. Because there's a whole lot going on, as we saw, if you would just take the time to look. OK, I have one last demo for you. And I have to say, this is entirely gratuitous, but it's a very fun example of networking. So I'm going to go ahead and show it to you all. So I don't know how many of you are not yet married, but if you ever need to propose to someone, this is an option that I want you to keep in your back pockets. OK, so recall the lonely printers. They are using, when it's saying, hey, I'm lonely, it's using a protocol that we haven't talked about before, ARP, which is the Address Resolution Protocol. And ARP's job is to map hardware addresses to IP addresses. What I mean by hardware addresses, inside this machine, there's a physical card through which the physical electronic zeros and ones get sent out through the waves out onto the internet. So this is at a lower layer than the routing layer than at IPs. So there's a distinct, unique MAC address, hardware address for each of my network cards. And ARP's job is to map those hardware addresses to IP addresses. And these are really important for a lot of reasons, but the big one is that they allow you to know on your local network who is who. So like if I want to talk to my printer locally, I use ARP to figure out where that machine is locally so I can send messages to it. Moreover, when you have a bunch of machines in your local network, there's typically a single machine, your gateway router, or this might also be called your access point, through which all of your data that's supposed to go out through the internet goes. So when I want to browse google.com, it's not like my machine directly talks to the internet. All of this traffic goes out through the gateway router, which is connected to the broader internet. So you use ARP to figure out who your gateway router is. So you're like, hey, who is my gateway router? ARP, tell me the hardware address with this IP address so I know where to send my packets locally so they can get out to the broader internet. So you use ARP to figure out who your gateway router is. Interestingly, this is mostly trust-based. So when I say, hey, who is my gateway router, it's assumed that the gateway router, the actual gateway router, will honestly reply, hey, I'm the gateway router. And we can sort of capitalize on this fact. So how about this? What if we could pretend to be the gateway router? Let's see what could happen. So we're going to do a couple of things here. The first thing I'm going to do is I have another machine on my local network that is set up to be a web server. It knows how to respond to HTTP requests. Moreover, we're going to tell it that it should know how to respond for requests that were actually sent to the gateway router. So for the IP address associated with the gateway router, we're going to know how to handle that HTTP traffic. So if it gets HTTP traffic, it's going to respond without actually going through the internet. It's going to respond with data that my web server has crafted to respond with all the time. We're going to start up Scapy, and we're going to craft some ARP packets that are going to say, hey, I know that nobody asked, but I am the gateway router. 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 When you want to send traffic to the internet, you are going to go through me, but not really to the internet. So we're crafting some packets, and again, Scapy is this really great tool for interactively producing and inspecting network traffic. So we send all these packets, and then my hapless boyfriend, comes home from a long day at work. He's like, I'm going to look up some resources on python.org. He's like, OK, going to go look some stuff up, and he types in python.org, and he presses enter, and this is what he gets. And this is all through the power of ARP being trust-based, and it being easier for us to construct a web server that responds with arbitrary content to requests. So once you understand networking, once you understand HTTP and IP and how this stuff works, boom, marriage proposal in the bag. Networking pays off. Awesome. Now I have to say that when I first crafted this proposal mechanism, I was not married. Now I am. Now, unfortunately, I was not the person who proposed, because if I had the opportunity, I totally would have used this tactic. But in compensation, I will say that when nerds get married, you have an opportunity to craft some very nerdy and delightful wedding rings. So this is actually what I'm wearing. And this, if people remember from their logic classes in high school or college, there are 2 universal logic gates out of which you can make all the other logic gates. And I have the NAND gates, and he has the NOR gates. So, oh, nerd love, I know. But for all of you folks who are unmarried, keep this tactic in your back pocket. OK, so we've answered our 4 questions. We've used Wireshark to inspect real traffic. We know how to propose by manipulating the trust-based ARP protocol. This is really just scratching the surface, right? I mean, networking is an endless topic. There are tons of endless pranks that you can pull on your flatmates. It's a really useful cross-cutting subject within computer science. So I definitely encourage folks to check out some of these tools, check out some of these libraries, and on your slow Saturday mornings, sniff your own wireless traffic as well.
What's etched on the inside?
Well, we couldn't leave that empty, right? So I can show you afterwards. So my name is Jessica. Let's call it Jess for short. His name is Adam. So if you take the zeros and ones that make up the binary of the ASCII representation, and you XOR them, put them back together, and then the hex of that, that's what's on the inside. I'll show you afterwards. I'm not kidding. Our jeweler wrote a blog post about our rings. He's like, I don't know where these kids come from. We are down the street from MIT. He's like, I actually get weird requests all the time from these kids. Anyway, I'll show you afterwards. OK, but so we've really just scratched the surface. So what are some next steps here? Well, there's this really cool series of books that include some of the things that we've talked about, including Twisted. They're called The Architecture of Open Source Applications. And they just discuss at an architectural level how various interesting utilities and libraries have been designed. And what's cool about these is that, A, you can read them for free online. Here are a bunch of the things that are covered. You can read them for free online. They're under a Creative Commons license. And if you buy the books, all the proceeds go to Amnesty International. Good deal. And then, moreover, hot off the presses, the newest entry in the series, the performance of open source applications, was released just in the last couple of weeks. Again, under that CC license, for free, all proceeds to Amnesty International. So check out that series if you're interested. I will also plug that I like Twisted, that utility that we use to write the web server, so much that I actually wrote a book about it. So this is my book. And because it is Cyber Monday, and O'Reilly is constantly running book deals whenever they can. So there's a book deal today if you buy ebooks through O'Reilly using this discount code. It's like 60% off or something. So if you want to learn more about writing web servers, IRC servers, email servers, and clients in Twisted, you can do it on the cheap today. Another thing, for folks who are going home for the holidays, the internet is really important. And as we saw earlier, the internet works because of an astonishing amount of global cooperation. These are companies who make money. Typically you're competitive to make money, but they actually cooperate. They work together to get your packets all over the world. The internet is a really political issue. The more people who understand the way that the internet actually works, the better informed society will be when we elect people and we make decisions about regulating the internet. So how about this? When you go home for the holidays, show your sister and your brother and your mom and your dad and your aunt and your uncle Wireshark. Talk to them at a high level or at a detailed level about how some of this stuff works. Because if only the technologists know how the internet works, that's not going to help anybody. There are a lot more people on this planet who need to know. So hey, when you're home for the holidays, have a quick discussion as you, do whatever it is you're doing with your family. Could be a good opportunity. And that is really it. That's my pitch to you. I hope that this is an inspiring introduction. It makes you want to go learn more. And that's really it. I will leave you with this map of the entire internet in 1977. Imagine the entire internet. And that's it. So thank you.